All right, for this next one, we have that the stopping distances for bicycles traveling at 20 kilometers per hour. This is per hour. Just gonna make a quick hint here. When it's written by with h to the power -1, anything to the power -1 is just gonna look like that. It goes to the bottom, goes to the denominator. So this is actually 20 kilometers per hour. Okay, it might look weird, but that's how it's written. So anyways, the stopping distances for bicycles traveling at 20 kilometers per hour are assumed to follow a normal distribution with mean this and standard deviation this. So under this assumption, find correct to 4 decimal places the probability that a bicycle chosen at random traveling at 20 kilometers per hour manages to stop in less than 6.5 and in more than 7 meters. So in the world of normal distributions, you need to open up your calculator and look at the tools that you have. So first of all, because you are in the world of distributions, you're going to go to this blue button here, the one that's on top of vars. See, so I'm going to put second vars, so I hit that distribution button, and these are the tools that I have. Now you will pretty much always work with the first three, okay, and it's important to be familiar with what these three things do. Now that being said, I have some notes on distribution that, if you want to take a screenshot or whatever, I suggest that you do. But basically, this is what each of these tools allows me to do. Let me find a little more space. These are the three main tools. See, so we have normal PDF, normal CDF, inventory normal. You can pause, take a second and read. But point is, in this case, we have to use normal CDF. See? So CDF, we use it whenever we have a range. All right. And so the range here, for example, in less than 6.5, it's going to be negative infinity until 6.5. That is going to be my range. See? And so normal CDF here makes sense. At the same time, you do not have to memorize what each one of these tools does. If you want to, you can. But I think it's far more important to understand that A, you face an over distribution, you open up the distribution tab, ¿cierto? You look at the tools, you remember that the first three are the ones I use, and you go one by one, see which one fits. For example, normal PDF, what does it ask? It asks for an x value. It is not asking for a range. It will give you the probability of a single x value. See? And so here, since it's less than 6.5, it is a range. Normal PDF does not work here. We keep going down our list. Normal CDF. See? Whoops. I'm still in PDF in that scenario. Let me try again. Now we're on normal CDF. See, so now we have a range. We have lower, upper, the mean, the standard deviation, etc. What I just showed you is the correct approach if you do not remember which function you have to use, which is, I mean, fairly common. See, but play around with it, get familiar with the calculator, and recognize what you need in what scenario. Here I have the ranges, right? And so as I said, the lower one was going to be negative infinity. Your calculator writes it like this, which is -1 E99. And just to prove a point, this is basically like it's like negative a million. Okay, that's the best way I can explain it. It's just a very, very big negative number. You do not have to write it like this whenever you want to put it manually. Just to prove my point, I'm just gonna put -1 with a lot of zeros behind it. So that is sort of like signifying negative infinity. Upper, we said it was 6.5. So I'm gonna put 6.5 here. This thing there is for median. I mean, sorry, for mean. We said that mean was 6.76. 6.76, and this other symbol here is going to be for standard deviation, which we said was 0.12. So we go ahead and paste. Boom, we end up with that number. So that number there is, I'm just going to write it over here, going to make a little bit of space, 0.0151. 30, blah, blah, blah. See? Awesome. Now in this case, it has to be correct to 4 decimal places. So that means I will count my decimal places one by one. 1, 2, 3, 4. That means that on this fourth one, I need to look at whatever's right next to it and see if I round it up or down. Because it's a 3, I just leave it as it is. So it stays as that. That is the answer for this first part. If instead of a 3, we would have had, say, a 5, my answer would have been this. Okay, so that is how the rounding part of it works. Yeah, that is for this first part. For this second part, it's pretty much the same thing, just that in the other direction. See, so instead of in less than, we have more than. And so again, I open up my distribution. We go to CDF because it's a range. And now my lower is actually going to be 7 because it is 7 to positive infinity, right? Anything more than 7. Whoops, apologies for that. Ba-ba-ba. And my upper, instead of putting negative a million like the other time, I'm just going to put positive a million. See? And that should do the trick. Basically, you're asking your calculator like 7 to a very big number. See? 7 to positive infinity. It all works. All right? My mean stays the same. My standard deviation does as well. Go ahead and paste. We end up with that. So that is 0.02275. And so now, a little bit like I was telling you earlier, for decimal places, right? So we have this first one, this second one, this third one, this fourth one. This 7 I have to compare to what's next to it. And look at that. It's a 5. So what does that mean? It turns into 0.0228. Awesome possum. So that is everything for part A. For part B, we have that 1,000 randomly selected bicycles are tested and their stopping distances when traveling 20 kilometers per hour are measured. Find correct to 4 significant figures. So now we're in the world of significant figures, not decimal places. The expected number of bicycles tested that stop between blah and blah. So again, we have a range. So that should already be telling us, okay, we are using CDF. So, whoops, distribution, CDF. We said it was going to be 6.5 and 6.75. That's my lower, that is my upper. Everything else remains the same. All right, so I end up with 0.451, 663. So now, since we're talking about significant figures, the way significant figures works is that when you enter the realm of like decimal places, that means anything to the right of 0, your first significant figure is your first legit number, your first non-zero, or so to say. So this would be my first significant figure, my second, my third, and my fourth. So just like before, we look at this 6, my fourth significant figure, see what's next to it, see if I round it up or down. In this case, I round it up. I end up with 0.4517. All right, awesome. We are almost done here. Why are we almost done? Because it is asking for the expected number of bicycles. See? And so here I am actually getting, I'm getting a decimal, I'm getting a percent. And so a little bit of context that maybe would have cleared up also part A a little bit. Part A is probability. See? And so basically you're looking at this normal distribution. And in this case, I am looking at, well, knowing that the median is at 6.76, I am looking at 6.5 and 6.75. See? And so the number that we just got, which I'm going to highlight in yellow, see, is actually a probability. So this right here has a probability of 0.45, which is the same as our probability of 45%. Okay? So point is, there's a 45% chance that you pick a randomly selected bicycle that has a stopping distance between 6.5 and 6.75. All right? Now in this case, they aren't asking for probability anymore. They're asking for the expected number. And so what is the expected number of bicycles in this case? Well, if there's a 45% chance that they pick it, and we are picking 1,000 of them, let's take that 45%, multiply it by 1,000, which is the same as taking this 0.4517 and multiplying it by 1,000. So that is, for like expected numbers or so to say, we end up with 451.7. So this is expected number of bikes right there. The biggest part we have to understand is that the first step is finding probability, and the second step is finding the expected number. So very, very careful. If it says expected number, do not forget that is what you're trying to find. See, you are not finding probability anymore. You're taking it one step further. For the second part, it's pretty much the same. We will go to distribution, CDF, because we're talking about range. My lower is going to be 6.75, as mentioned earlier. My upper will be 7. Everything else remains the same. Boom. We end up with that number there. So here we have 0.51045. We'll put the 6. Why not? All right, so in respects to significant figures, a common mistake that people do, and this is what I was trying to explain earlier, but this is a better example now, is that they think 0 is not a significant figure. And so significant figure is the first number that is not a 0 that shows up. For example, and I think this is going to leave it very clear, if I ask you for two significant figures of, let's say, this number here, your first significant number is not this 0, it is this 1. See? So this is your second significant figure. You compare it to this, you end up with that. Okay? So your significant figure does not count the 0. However, if I were to have a very similar scenario, and I have it like this, and I say, hey, do this to two significant figures, sure, you don't count this one, but you do count this one, and you do count the one after that. Okay? So two significant figures here would actually be that. All right? So there's this whole thing of when do you count the 0, when do you not? You do not count the 0 if you have not run into your first legit number yet. See? So in this scenario, we already ran into our first legit number. That means that this 5 over here is going to be my first significant figure, this 1 the second, this 0 the third, this 4 the fourth. See? Since it's correct to 4 significant figures, that means I take this 4, compare it to the 5. Because it's a 5, I round it up. So I end up with 0.5105. Again, this is in percent. The expected number is going to be this multiplied by 1,000 because we are looking at the expected number of bicycles. 1,000 randomly selected bicycles, that's why they 1,000. We end up with just around 510.5 bicycles. So that is for the second part. Bada bing, bada boom. Then they tell us that the measured stopping distance of 1,000 bicycles are given in the table below. So this is what was observed. Okay, that's a keyword here. This is what was observed. So less than 6.5 gave us 12. Between 6.5 and 6.75 gave us 428. Yada, yada, yada. See? Cool. Then they tell us that it is decided to perform a chi-squared goodness of fit test at the 5% level of significance to decide whether the stopping distances of bicycles traveling at 20 kilometers per hour can be modeled by a normal distribution with mean, blah, 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 standard deviation, blah, blah. So, part C, state the null and alternative hypothesis. So, for the null hypothesis, I'm just going to put a text here, actually, it's going to be way easier. For the null hypothesis, for part C, okay, we're going to say that H0, in this case, has to be that the stopping distances can be modeled by n. Actually, I'm going to draw that next part. Can be modeled by, let me erase this, make a little bit of space for my homies. Can be modeled by n, parentheses, 6.76, comma, 0.12 squared. All right, so that is like the big thing for getting a point in this part of the problem. Because it's making reference to a normal distribution, right? Whether it can be modeled by a normal distribution, you have to write it how it corresponds. See, and so that's like a hard part here. The normal distribution, you put like a fancy n, the parentheses, you put the median, and next to it, you put the variance, which is standard deviation squared. Okay, so this is actually variance, see? Which again, as I said, variance is standard deviation squared. That's why you have the 0.12 squared over here, okay? So that is kind of like where they try to catch you in this part of the problem. So anyways, HO is going to be, it's generally what the exercise gives you. HO is generally going to be what the exercise is looking for. And that, in the sense that you're trying to see if it can be modeled. Okay, so here we're going to put can be as well. And then for this next part, we're going to put that H1 is basically the opposite of that. So stopping, whoops, that was a little loud. Stopping distances cannot be modeled by the same thing. See, so the same thing being n 6.76, 0.12 squared. See, so as long as you're consistent in this sense, that h0 is going to be pretty much what the exercise gives you, and h1 is going to be the opposite of that by simply adding a negative. So we'd say cannot, ¿cierto? We end up with part C. For part D, we need to find the p-value for the test. Now, I can give you the answer right away, or I can give you like the approach, and I think the intuition of the approach is way more important. So here we are performing a test of chi-squared goodness of fit. See? Now that right there is a little more important than what you think. Goodness of fit. If we take the first letter of each, we end up with GOF. Aha. Might sound a little familiar, right? We go to stat test, because this is a test. We see which tests we have, and we find a chi-square test. So a lot of people reach the chi-square test and they say, booyah, I'm good to go. But it's goodness of fit, it's GOF. Scroll one more, there it is, GOF. What's the difference between the two? GOF is asking for lists. Okay. Chi-squared is asking for a matrix. These big letters with parentheses are a matrix. The other one is list. Here we have literally just one list here, number of bicycles. And so it makes sense that we use GOF because list. Basically, the intuition I'm trying to say is that GOF equals list. Not GOF, I don't know how else to put it, is going to be, well, you can say matrix or you can say not list. Okay? So that's the intuition of when to use which. In this case, we are working with GOF. So, again, we open up our calculator. We see what it is asking for. Let's go step by step real slow. GOF, it asks for observed and expected. So my observed, as I said way earlier, is going to be right here. All of these is what was observed, not what was expected. As it says here, the measured stopping distances is what gave us here. See? So for observed, we have that table there. And now we need to find the expected one. The expected one is not given to us, but we can find it. So, writing down here, we have less than. Actually, maybe it's going to be a little faster if I just write it out. Essentially, we need to find, we have the range here, then the probability, and then the expected. Okay? So, the first range is less than 6.5. See? Then we have the probability of that, which we found in part 4.a, right here, less than 6.5, which was 0.0151. Okay? And my expected is going to be, well, 1,000, because it is the distances of 1,000 bicycles, right? Let me raise this a little bit so that we can all see and be on the same page. This is a chi-square test having in mind 1,000 bicycles. So my expected value is going to be 1,000 times my probability. See, in this case the probability is 0.0151, and that'll give me a certain value. Okay, that certain value is going to be 1,000 times 0.0151. Boom, 15.1. Okay. So my expected table is now beginning to form over here. All right, so that is for less than 6.5. So that is the range. The probability is that, and my expected has to be, well, this whole thing on the right side. See? That is the approach. All right. The next range we said was between 6.5 and 6.75. So I'm just going to put I mean, you guys know what's going on now, 6.5 and 6.75. What is the probability of that? We found it earlier in this part here. We said it was that number there. See? So that number there, simplified there, 0.4517. We're going to take 1,000, multiply it by that. We end up with roughly 451.7 bikes. And we keep going. The next range was between 6.75 and 7, which is part B right there. How convenient. I erased it by accident, but I recall that it was this. See? So this one is from here to here. The probability of that was 510. All right, at this point, you must have realized what's going on. See? Again, we're doing this to build. Whoops, apologies for that. But yes, we're doing this to build the expected table. So then we can put the observed table and the expected table into our calculator, and we're good to go. And for more than 7, so it's going to be from 7 to positive infinity, we found it right there. See? We said that it was 0.0228. So here we're going to put 0.0228. Whoops, I missed the point over there. We do 1,000 times this, blah, blah, blah. We end up with 228, 22.8. All right, so this is my expected table. Just so that we're on the same page in terms of its intuition, we take the same ranges. See, so we take all of these ranges here, which are the same ranges that I have there. I find the probability of each of these ranges, which is from part A and part B. All right, awesome. All of these. And we find the expected value of this, expected being 1,000 bikes, because it's what the context of the problem is giving us. That's why we multiply by 1,000. And we generate the expected list there. See? So now we are ready to open up our calculator, go to stat test, scroll down to Goff, and observe expected L1, L2 respectively. So I need to go to stat now, edit. So stat edit, go to my list. Observed is going to be the first one. So I go ahead and pop those guys in. Expected is going to be the second one. I pop those guys in as well. And now we go ahead and actually do the test. Boom, boom, boom. df in this case is going to be 3. That is degrees of freedom. It's basically always going to be your rows minus 1, okay? Or your columns minus 1, depending on the context. In this case, I have 4 of them, so it's going to be 4 minus 1. Calculate. We end up with this. So the p-value for this test, part D, is going to be what we just got on our calculator, which is 0.0726542. All right. So that is for part D. If you want to show your work, you basically put this window into your calculator, or you can also show all your work with the expected stuff. See? For part E, we need to state the conclusion for the test and give a reason for our answer. Now, in this case, we have a level of significance. Okay, so this is how we can see whether our answer is legit or not. Essentially, we need to compare this level of significance to our p-value and see what happens. So in this case, our level of significance, right, which is 0.05, is it greater than or less than our p-value? Well, our p-value is 0.0726542. In this case, our p-value is greater. So if our p-value is greater, and unfortunately this is one of the things you just kind of have to memorize, if our p-value is greater, then that means that there is insufficient evidence to reject HO. The other way that you can phrase it, if you'd like, is that you accept HO. All right? Either one of these works. Point is, you have to compare your critical value to your p-value, and this is the proper way to conclude it. So, that being said, that is part E. That is how you do number 4.